Okay, so let's go into some different applications. One more application of these registers. Now you have seen USB ports. So these USB ports are serial ports. What do we mean by serial ports? Like, you see that when you connect your USB drive, okay, so USB drive will have large amount of files. It is these days it will not come less than 4 GBs or 8 GBs, or sometime you can it could be even more than that. Now if you have seen inside, or you have seen the port of this USB, you will see there are only 4 wires. 2 wires are VDD and ground. That's why if you plug in your USB, your phone acts, this USB cable acts like a charger. The other 2 pins are there to transfer 1 bit of data at one time. So because although your USB disk or USB drive may contain GBs of data, but only 1 bit is transferred at one time. So at the receiving end, we would like to have movies stored in our USB drive, or maybe lectures stored in USB drives, or PPT stored in USB drive, but it is being transferred bit by bit. Eventually we would like to read the bytes, we would like to read the characters, maybe words, maybe whole files, but it is one by one. So what do we do? How do we receive this serial data? That's why it's called serial, because data is being received bit by bit. Now when we are receiving it bit by bit, there are 2 possibilities. Now either we take least significant bit first and then most significant bit, and then we can store them in registers, and when enough number of bits are there, let's say we would like to store 32 bit of data. So once 32 bits has been received, then we can read it out as a parallel register, or as a 32-bit number. Okay, so how can we do that? So what has been seen, you can use certainly flip-flops. But if flip-flops are connected in certain manner, or you eventually would like to store them in registers, but these registers has to be connected in certain manner so that we can read them efficiently. They're being fed one by one, but we can read them efficiently. We can read all of the data in parallel, so we can read like 32 bit of data at once, but they would be fed bit by bit. Okay, so can we use registers efficiently? Because the way we have created previous registers, they were parallel in, parallel out. You have to give, there were n number of inputs to my register. D in was a n bit number. Here, can we have, the question here is, can we have single bit as an input here? Okay, so let's see, if I would like to do in registers, how can we do that? So instead of taking 32-bit number, which can be like whatever solutions we are developing here, it can be scalable to that also, but let's take a 4-bit as a number. So we are trying to store 4 bits in a serial in manner, one by one. Because there are 2 mechanisms, either we can take first least significant bit, or more significant bit. Let's take least significant bit first. Okay, so what we can do is, we can take this least significant bit and give it to a register, give it to a flip-flop. Now in this flip-flop, we are giving this input, least significant input. I said it's a 4-bit register, so I have 4 flip-flops. D3 is the most significant flip-flop, and I'm connecting my D input, the single bit input, serial input, to my most significant flip-flop. The output of this flip-flop is connected to the next flip-flop, D2. Then the output Q2 is connected to D1 flip-flop, flip-flop at D1 position, and the Q1 is connected to the next, the least significant D0 input of the flip-flop. So there are 4 registers, but they are connected in this manner that my output, so my serial input is connected to the most significant flip-flop, and then each output is going to the lesser significant flip-flop till the end. Now, because output is connected to the next flip-flop, this is also called shift registers. And this is also called serial in register because there is only single input. D in is a 1-bit input, and which is being fed to a 4-bit register. It's quite generic. Instead, if you want to take 16-bit register or 32-bit register or 64-bit register, it can keep on cascading like this. Will it work? How will it work? So all these are questions which are coming to my mind. So let's see, by taking an example and by flipping the bits. Okay. So let's consider a clock period, and let's also consider my D in clock, or D in as an input. Now further consider that my clock is positive edge is the active edge. And if I see what is my input is, this is 0, this is 1, 1 and 0. Now because this is the least significant bit, so this is bit 0, bit 1, bit 2 and bit 3. Okay, so if that is the case, now let us see what would be the, so if this is the input, what would happen at Q3. So in Q3, this 0 would be sampled at this time. Because 0 is sampled, my output for this one clock period is going to be 0. Now in this active edge, 1 is sampled, so 1 would be the output for next one clock cycle. Next active edge, 1 is being sampled, so 1 would be the output here for next clock cycle. And at the end of this 4th clock cycle, because 0 is sampled, this would be the output. So this would be the output for my Q3. Now Q3 is given as an input to D2. So what would be the output at Q2? So at Q2, everything is shifted by 1 clock cycle. So whatever was the input here, that would be the output after 1 clock cycle. So you see, we can quickly check. So at this positive edge, because Q3 was 0, Q2 would be 0 for 1 clock cycle. Similarly, at this positive edge, Q3 was 0, so my Q2 output will be there 0 for 1 clock cycle. Similarly, at this positive edge, because this was 1, output would remain 1 for 1 clock cycle, and similarly at the this particular positive edge, my output was my input was 1, so output would remain 1 for 1 clock cycle. Similarly, for Q1, my Q2 output is given as a input to this flip flop as a D1. So D1 is Q2. What the output would be? Output is again shifted by 1 clock cycle. Okay, so 0 for first clock cycle, the second clock cycle, third clock cycle, and here it is 1 because in this active edge, this 1 is being sampled. Similarly, if I see Q0 for all the clock cycles, it's going to be 0. So if I see this way, I can see that this particular 0 has reached at cycle number 4 in Q0 as a Q0 output, and this is 1, this is 1, and so this is my bit 0, this is bit 1, this is bit 2, and this is bit 3. So we have received them in the reverse order. Although D in was connected to most significant register, most significant bit of my flip-flop, but because it is cascaded, my output was connected to the next input, similarly the next output was connected to the further next input. So that's why we were shifting the value of D in to the right direction every time. We can also call this particular register as shift right register. We are shifting the output in the right direction every 1 clock cycle. Incidentally, here input was only D in, only single bit was the input. So we could have designed like this. Now one more question which comes to my mind. So here my clock as well as D in both are shifting at the same time. How is it possible? And my output is still correct. So here my assumption is that my my hold time is 0, but setup time is non-zero, and propagation time is also considered as 0. So to make this circuit looks simple. However, usually my as D in would be, so there would be certain delays involved here. So because of those delays, my I can make sure that the so if setup time is non-zero and propagation time is also non-zero, then also it would work correctly. Yep. So to make this diagram simplistic, we have taken setup time as well as propagation time, hold time as well as propagation time as 0. Good. So this way we can use this serial input as serial input, but still we can use these registers. Now Q0, Q1, Q2, Q3. From there we can always read out the values. We can always read out the values and we can read them parallelly. So whenever we would require to read this 4-bit value, so let's say if it's a 32-bit register, then it would require 32 cycles, because each data would require 1 clock cycle. After 32 cycles, we can read all the 32-bit data at once and then reuse them wherever it is required. Okay, so with this, let's move on to the next one. Now here the summary of the previous slide was that we could understand this serial in kind of a operation is also similar to a shift operation, because we are shifting the input every time. All the inputs are getting shifted. If we see the shift operation, the shift operations are quite popular in binary arithmetic. So we are switching the gear. So basically let's quickly understand how the shifting operations typically works in binary arithmetic. So let's say let's talk about shift right operation. So shift right operation means, let's say I have some number and I'm shifting it right. So shifting it right means this is my least significant bit, this is most significant bit. When I'm shifting it right, then it will become 0 1 1 0. What I have done is, whatever was the bit here, I have discarded. Rest of the things I have shifted it in the right direction. The question here will be that what should come in the empty space here. In the empty space here there would be two choices: either we put 0 or we put 1. What is the reason we'll put 1? So since there is no reason, let's put 0. So now let us also see what this number is. And so if you see this particular number 0 1 1 0 is actually equal to 0, this is 1, this is 2, this has a weight of 4, this has a weight of 8. So that means this number is 12, this number is 6. Now by shifting right, I am able to divide the number by 2. If the initial number was 12, now after dividing it becomes 6. So that means by shifting right by one place, I am able to divide it by 2. Okay, so will it always work? So let's say if there was a 1 here which we were dropping, so instead of 12 it was 13, but because we were shifting right, that 1 would have been dropped. after dividing 13 by 2, it would still be 16, because whatever we are dropping is actually a remainder. Okay, so in other words, whenever we are dividing by 2, by shifting, if we are doing a division by shifting, then we are taking the floor of that value, floor of the result. Okay, so let's take one more example. Let's say I have 1 in the most significant place. Now I am shifting. After shifting, it will become 1 1 1 0. Now further, there is a question: what should be kept here in the empty place? So whatever was in the right, that we have discarded, but in the most significant place there is a empty space, whether there should be 0 or whether there should be a 1. Let's say why it should be 1. Now consider that this particular number is a negative number. If it is a negative number, then this 1 was not representing the magnitude, but it was representing the sign. If I am shifting it right, then the sign of the number cannot change. It has to be same as the previous sign. So there is a possibility that there can be 1 here. But in what cases there should be 1? Whenever number is signed, then I say that whatever is most significant bit, that should be kept here. This particular method of shifting is called arithmetic shift right. Arithmetic shift right means I am assuming this number is in 2's complement form. It's a negative number. Because it's a negative number, it could be positive as well as negative, but it's a 2's complement number. Because it's a 2's complement number, the most significant bit represents sign. If that sign was 1, here we have to keep 1. If sign was 0, here we have to keep 0. So let's consider this also as a 2's complement number. Because it was 0 here, so we have kept 0. So let's look at the numerical numbers also. If we see this 1 1 1 0 0, if I take 2's complement, then I will see that this particular number is actually -4. And by shifting right, this number become -2. So that means here also this definition is working correct, that it's actually division by 2. -4 divided by 2 is -2. Okay. But there is also a possibility that this number is not 2's complement number, but it's an unsigned number. If it is an unsigned number, then this particular number represents it's 16 plus 8 plus 4. 16 plus 8 is 24, 24 plus 4 is 28. So this number represents 28, and then this number should represent 14. So that means there has to be a 0 here. So if it is an unsigned number, then we call it logical shift right. In case of logical shift right, whatever we are filling here is always 0. But in case of arithmetic shift right, if the input number has the most significant bit, whatever is the most significant bit, that would be replaced in the shifted number also. So this was shift right operation. On the other hand, there could be a shift left operation also. In shift left operations, we are pushing all the bits in the left direction. So let's say 0 0 1 1 0 was the input, and then shifting it by one place, it will become 0 1 1 0 0. Now all of bits are being shifted here. Now whatever was the most significant bit, that's being thrown away, and we are always adding 0 in the least significant place. So this shifting left is essentially a multiplication by 2 operation. So here it was 6, and after multiplication by 2 it became 12. So it's multiplication by 2. What would happen if there is a one more shift operation? So if I do one more shift operation, then this 12 should become 24. But if it's a 2's complement notation, then this could be minus 16 as well. What is the correct value? What should be the correct thing to represent? Now, because in 32 in this 5-bit numbers, sorry, this is minus 8. So in 5 bits number, the value or the range of numbers could only be from 15 to minus 16, because the range in this particular number 12 cross 2 24 is outside the range. This has become an overflow. So overflow is an error. Although this number could be a negative number, if we are trying to put it as a positive number, if it was a sign notation, then this become an overflow. We have to check whenever we are shifting left. We have to say that if most significant bit or the sign has changed, that means there is an overflow. Okay, so but if there is no overflow, it will ideally work correctly. Correct? So yes. So this is how these shift operations can be done, and these shift operations are very important core part of our digital arithmetic. We have seen that while doing addition, while doing multiplication, these shift operations are quite much required, both logical shift operations as well as arithmetic shift operations. Now, in the previous slide, we have seen that this serial input can be done efficiently by registers where output is cascaded. My output is given as input, the next flip-flop. So that means my registers can also work in a very efficient way, like a shift registers or shift. They can be helpful to implement these shift operations. Okay, so if we have to implement a shift right operation, let us see that how a shift right operation, this shift right operation can be done using shift registers. Now this diagram is similar to the previous serial in shift register. So here each output is fed as an input to the next register. Now this output Q2 is given as input to D1, Q1 is given as input to D0. Now given this kind of a setup, can we use this as a regular shift register? I suppose yes. There is the only thing we have to make sure that to make arithmetic shift operations correct, we have to make sure that the next, whenever we are shifting, this Q3, because this is the most significant bit, this most significant bit can be given as an input to my most significant register bit. And then if we are doing left shift operation, then 0 would be given to as an input to my most significant bit, or the whatever was the sign bit, that would be given as an input to my least significant bit, sorry, the most significant bit. So this LSR, whether it is a logical shift operation, if it is logical shift register, then we have to say 0 would be given, otherwise the whatever is the Q3, that would be given as a, or the whatever is the most significant bit, that would be given as the input. Now the next question is how about we can give input. So here typical shift registers may not be serial input. They would be parallel input, parallel output, the first register which we have studied in today's class, that all the input would be given in parallel. So outputs are certainly parallel. So Q3 would be read from here, Q2 would be read from here, Q1 and Q0 will be read from here. But what about the input? So that means input also will come in parallel. So D3, or basically D3, D2, D1, D0, there should be 4 inputs here. So then what should we do? Let's think it for a while. Maybe yes. So we may have to have additional multiplexer here. Here there should be a mux. Here there should be another input of this mux. At all the input there has to be a mux. Either it is coming from the output of this shift register, output of the previous flip flop, or it is coming as a input. Who will decide? If the load is there, if we would like to load the shift register, then we are taking it from the data input. Otherwise, it can work like a shift register. So let's see in form of diagram how does it look like. So yeah, so this would be the registers, the multiplexer introduced. Now when we are introducing this multiplexer here, instead of 2 input, there are 3 inputs. D3 is given as input to this mux. Similarly, D2 is given as input to this mux, but output Q3 is also given as the another input to this mux. So you see, D1 input could be either Q2 or it could be D1. Similarly, for all other cases, all these multiplexers are controlled by control input C. Here, this is controlled by control input C1. Now, all these chip enable or clock enable are controlled by my control signal C2. So, if I see here, because it's a 3 input mux, there has to be at least 2 inputs. Input 0 and input 1 means that we are performing some shift operation. Okay, while input 0, 1, 2, if input 2 is there, so C1 is going to be a 2-bit control, and in this 2-bit control, you will see that control 0 would take Q3 as an input and control 1 will take 0 as an input. So that means in both these cases we are shifting. And because this is 0, this is 1 case, so we can take left shift. Either if we are performing left shift operation, then we can take the 0th bit as that. And if we would like to perform a load operation, then we can make first bit of C1 control as 1. So that means D3 would be taken as D3 would be given to input D3 of this flip-flop. Okay, so similarly, this C2 control, that means when we have to make this clock enable, this clock enable would be 1 if there is either we would like to load or we would like to shift. In either of these cases, this clock enable has to be 1. Okay, so otherwise there is no clock enable, so that means my register value would remain as such. Now all of these C signals which are deciding whether to take input from previous flip-flop or D2, it would be decided by this control signal. This control signal could be a load one. So if load is 0, then it would be taken from this Q3, or if load is 1, then it's taken from D2. Similarly for all others. So this is how we can design a 4-bit shift register which can load the input parallelly, as well as which can shift all these bits from right from left to right. Okay, so can we design a universal shift register? A universal shift register can shift in left direction as well as shift in right direction, can also load data, it can also retain data. Okay, so if we think it this way, and let's think from this particular circuit also, can we extend this to make a universal shift register? So if we see this circuit is essentially iterative in nature. So basically, if we are able to design one particular cell, all other cells can be replicated. The only exception would be boundary cells. Like here in boundary cells, we have different control structure. Okay, so if that is so, can we design it? So let's try to see how we can design a universal shift register. So in case of a universal shift register, if I would like to shift left, if I would like to shift right, then my input to each of this ith D flip-flop would be coming from Qi plus 1. So let's say this was D2, then this is coming from Q3. And if it was a shift left register, then this the next input, one of the input has to come from, if it's a di, then it should come from di minus 1. So let's say if it is d2, then it should come from q1. If I would like to retain, or this is a case of, you are saying this is a case of clock enable, or we would like to retain, then we can take the input directly from the output of this register itself. And in case we would like to give parallel input, or we would like to load the data, one of the input should also come from data input, ith of data input, and my control will decide. Because there are 4 different inputs, my control could be a 2-bit structure, C0 and C1, and if it is 0 0, it could be shift right, that means the input is qi plus 1. If it is 0 1, it could be shift left, that means the input is qi minus 1. So sorry, 0 0 means qi plus 1, and 0 1 means shift left, and it is qi minus 1. If the control input is 1 0, so that means my input is qi. In case of 1 1, I would like to load the data, so this di is going to be my external input. So this way I can design my generic or iterative circuit for my universal shift register, with the exception to boundary cells. What would happen in the boundary cells? There would be C, let's say it's a n bit register, my n minus 1, or the most significant bit or most significant flip flop. That flip flop here, we'll say that if it is left shift, so here this qi plus 1, or basically this particular input, will come from another multiplexer, where it could be 0 if it is left shift register, a left shift operation. If it is qi, it could be qi if it is arithmetic shift operation. Similarly, in case of cell 0, that will also be a boundary cell. In case of cell 0, my qi minus 1 would be 0. So basically here, because there is no q minus 1, in case of d0, this is going to be q minus 1, because there is no q minus 1, so essentially it will become, we can directly tie it to 0. So that way my cell 0 will be a boundary cell, it would have slightly different implementation. So this is how we can make a universal shift register, and this is if you want to extend it further, you can design maybe a circular shift register. You can also design a parallel in serial out register. One more similar exercise could be that in universal shift register, there could be another case where it could be a serial in parallel out register, as well as parallel in serial out register, as well as parallel in parallel out register plus shift register. So that will make a completely universal shift register. Okay, so with this I would like to summarize this lecture. In this lecture we have seen what is a register, what could be its different applications, and we have also seen a particular case of shift register, which is a shift. We have seen a particular type of register as a shift register, and we have seen that this shift register could be quite interesting in doing different kind of arithmetic, like addition, arithmetic like shift by multiplication by 2, division by 2, maybe arithmetically or logically. Okay, so with this I would like to close. Thank you very much.